Here is a question that every physics teacher in Australia has been asked, and here is the answer almost every physics teacher in Australia has given. The question, why does mass create gravity? The answer, it just does. That is it. That is the answer. Mass creates gravity because mass creates gravity. Now, to be fair to your teachers, that answer is not entirely their fault, because this question cuts to the very edge of what physics currently understands. And the honest answer is genuinely complicated. But here is what bothers me. Your textbook did not just fail to answer this question, it failed to even ask it. It handed you the equation, F equals G times M over R squared, and moved straight on. Without ever stopping to ask, but what is mass? What is it about having mass that makes space-time curve? And here is the really confronting part. Is mass even the right thing to say causes gravity? Because according to Einstein's field equations, mass is not the whole story. Energy curves space-time. Pressure curves space-time. Momentum curves space-time. Mass is just one ingredient, and your textbook never told you that. Today, we fix all of it. G'day and welcome back to Curious Physics AU, the channel that takes physics seriously enough to follow the questions all the way to the bottom, even when the bottom is very deep indeed. I am Abdullah, and today we are tackling a question so fundamental that most physics courses never go near it. Why does mass create gravity? To answer it properly, we need to journey through three distinct layers of understanding. First, what is mass actually? Second, what really sources gravity according to Einstein? And third, why does having mass, or energy, or pressure cause the geometry of space-time to curve at all? Fair warning, by the end of this video, your understanding of both mass and gravity will be permanently and productively changed. That is not a threat. That is a promise. Let us go. Before we can ask why mass creates gravity, we need to establish what mass actually is. And here is where your textbook almost certainly let you down for the first time. There are actually two distinct concepts that both go by the name mass, and conflating them, as most school courses do, obscures something absolutely crucial. The first is inertial mass. This is the mass in Newton's second law, F equals ma. Inertial mass is the measure of how much an object resists acceleration. The more inertial mass something has, the harder it is to change its velocity. A cricket ball is easier to accelerate than a car, because the car has more inertial mass. The second is gravitational mass. This is the mass in Newton's law of universal gravitation. F equals G times M over R squared. Gravitational mass is the measure of how strongly an object sources and responds to gravitational fields. It is the gravitational charge, analogous to electric charge in electromagnetism. Now, here is the profound experimental fact that most school courses gloss over entirely. Inertial mass and gravitational mass are exactly equal to every decimal place ever measured, in every experiment ever conducted. A cannonball and a feather, in a vacuum, fall at exactly the same rate. Not approximately the same, not roughly the same, exactly the same. This was demonstrated beautifully at the Apollo 15 moon landing in 1971, when astronaut David Scott dropped a geological hammer and a falcon feather simultaneously in the lunar vacuum. They hit the ground at exactly the same moment. Now, why are inertial mass and gravitational mass identical? Newton had no explanation. He simply observed that they were equal and moved on. Einstein made that equality the cornerstone of general relativity, his equivalence principle. He elevated it from an unexplained coincidence to a fundamental principle of nature, but it still does not tell us what mass is at the deepest level. For that, we need particle physics. We need the Higgs field. The standard model of particle physics, our best current description of the fundamental building blocks of matter, faced a serious problem for decades. Its equations worked brilliantly, but only if all the fundamental particles were massless. The moment you tried to give particles mass in the equations, the mathematics broke down completely. The predictions became nonsensical. In 1964, British physicist Peter Higgs, along with several other physicists working independently, proposed an elegant solution. What if there is a field permeating all of space, with which particles interact? And what if the strength of that interaction, the degree to which each particle couples to this field, determines how much mass that particle has? This is the Higgs field. Think of it this way. Imagine the entire universe is filled with an invisible substance, like honey, spread uniformly through every point in space. Now imagine different particles moving through that honey. Some particles interact with the honey very weakly. They slip through almost without resistance. Those particles have very little mass. Photons, particles of light, do not interact with the Higgs field at all. They have zero mass. That is why light travels at the speed of light. Other particles interact with the Higgs field very strongly. They get bogged down. They resist acceleration. Those particles have large mass. The top quark, the heaviest known fundamental particle, interacts with the Higgs field with extraordinary strength. So mass at the quantum level is not an intrinsic property of particles. It is the result of how strongly each particle interacts with the Higgs field that permeates all of space. In 2012, the Large Hadron Collider at CERN in Switzerland detected the Higgs boson, the particle associated with the Higgs field, confirming the theory experimentally. It was one of the greatest experimental achievements in the history of science. But, and this is the crucial point, the Higgs field explains where the mass of fundamental particles comes from. It does not fully explain why having mass, or more precisely, having energy, causes space-time to curve. For that, we need Einstein's field equations and something called the stress-energy tensor. Here is the part that your school textbook almost certainly never showed you, and it fundamentally changes the picture. Remember Einstein's field equations from our previous video? GMN plus LGMN equals 8πIg over c to the fourth times tim. The right-hand side, tin, is called the stress-energy tensor, and it is the thing that curves space-time. Now, what is in the stress-energy tensor? Your textbook might have told you mass curves space-time, end of story. That is wrong, or at the very least, dangerously incomplete. The stress-energy tensor contains energy density, momentum density, energy flux, momentum flux, and pressure in all three spatial directions. All of these things curve space-time, not just mass. Example 1. Pure energy curves space-time. A box filled with photons, particles of light, has zero mass. Photons are massless, but the photons carry energy, and that energy contributes to the stress-energy tensor. That box of light curves space-time. If you shine a powerful enough laser beam, it generates a gravitational field, unmeasurably tiny with any laser we can build, but real. The physics is unambiguous. Example 2. Pressure curves space-time. Inside a neutron star, the densest objects in the universe short of black holes, the pressure in the core is so extreme that it makes a significant contribution to the gravitational field, not just the mass. The pressure itself curves space-time. This has real consequences. When a massive star collapses toward a black hole, as the density and pressure increase, the additional space-time curvature from pressure accelerates the collapse. Pressure, in trying to resist gravity, actually adds to it. It is a runaway effect that makes the collapse inevitable. Example 3. Kinetic energy curves space-time. A moving object has more energy than the same object at rest because of its kinetic energy, and therefore it curves space-time more than when it is stationary. Your car moving at highway speed, let us say on the Hume Highway between Sydney and Melbourne, curves space-time very slightly more than your car parked in your driveway, not enough to notice, but enough for the physics to insist upon. The source of gravity is not mass. The source of gravity is the full stress-energy tensor, energy, momentum, and pressure in all their forms. Mass is simply the most common and most dominant form of energy we encounter in everyday life via Einstein's famous E equals mc squared, but the universe is not so simple as to let mass have all the fun. This is where Einstein's most famous equation becomes genuinely important, not just as a cultural icon, but as a precise physical statement. E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are the same thing. Different forms of the same underlying physical quantity. Mass is concentrated energy. Energy is diffuse mass. The c squared factor, the speed of light squared, is an enormous number, about 9 times 10 to the power of 16 meters squared per second squared, which means a tiny amount of mass corresponds to an enormous amount of energy. 1 kilogram of mass, if fully converted to energy, releases about as much energy as 21 megatons of TNT. The largest nuclear weapons ever built released energy from converting only about a kilogram of matter. The sun converts about 4 million tons of mass into energy every single second through nuclear fusion. That energy, radiating outward as light and heat, is what warms Australia's beaches, powers our solar panels, and sustains all life on this continent. Mass converted to energy. Energy radiating across 150 million kilometers of space-time, arriving here as sunlight. Now, here is the gravitational consequence. If mass and energy are equivalent, and if the stress energy tensor source is gravity, then mass curves space-time because mass is energy, highly concentrated, localized energy. The question, why does mass curve space-time, becomes why does energy curve space-time? And that question, as Feynman would honestly acknowledge, does not yet have a complete answer at the quantum level. We know how much energy curves space-time. Einstein's equations tell us precisely. We do not yet fully understand why energy curves space-time at the deepest level of reality. That is quantum gravity again, knocking at the door. Here is something that very few people, including many physics graduates, fully appreciate. Most of the mass of the matter around you does not come from the Higgs field. The Higgs mechanism explains the mass of fundamental particles, quarks, electrons, and so on. But protons and neutrons, which make up almost all the mass of atoms, are not fundamental particles. They are composite. Each proton is made of 3 quarks bound together by the strong nuclear force. And here is the extraordinary fact. The combined mass of those 3 quarks is only about 1% of the mass of the proton. Where does the other 99% come from? Binding energy. The gluons, particles that carry the strong nuclear force between quarks, are massless, but the energy of their interactions, the energy of the strong force field binding the quarks together, contributes to the mass of the proton via E equals mc squared. Roughly 99% of your mass, every kilogram of you, is not the intrinsic mass of the particles you are made of. It is the energy of the forces binding those particles together. You are mostly energy, disguised as mass, via E equals mc squared. And all of that energy, mass energy, kinetic energy, binding energy, contributes to the stress energy tensor. All of it curves space-time. So the question, why does mass create gravity, has a layered answer. Mass creates gravity because mass is energy. Energy curves space-time because it appears in the stress energy tensor on the right-hand side of Einstein's field equations. And the stress energy tensor curves space-time because, and here we reach the honest frontier, that is what the mathematics of general relativity requires, and general relativity matches every observation ever made. The deepest why does energy curve space-time at all, remains one of the most profound open questions in physics. We are at the edge of the map. Here, there be dragons. Now, if pressure curves space-time in the same way energy does, what about negative pressure? This is where things get genuinely wild. Normal pressure curves space-time in the same direction as mass and energy. It contributes to gravitational attraction. Things pull together. But negative pressure, tension, curves space-time in the opposite direction. It contributes to gravitational repulsion. Things push apart. And here is why that matters enormously. Remember the cosmological constant, lambda, that Einstein added to his field equations and then called his greatest blunder? The one that came back in 1998 when we discovered the universe's expansion is accelerating. Dark energy, the mysterious substance that makes up roughly 68% of the total energy content of the universe, behaves exactly like a fluid with negative pressure. Its energy density is positive, which should cause gravitational attraction, but its pressure is negative, and that negative pressure term in the stress energy tensor dominates. The net effect is gravitational repulsion. Dark energy, whatever it fundamentally is pushing the universe apart, accelerating the expansion of space itself, not because of a mysterious new force, but because negative pressure, which is just as real a contributor to the stress energy tensor as mass or energy density, curves space-time in a repulsive direction. The same mathematical term that describes the pressure inside a neutron star contributing to its collapse also describes the negative pressure of dark energy driving the accelerating expansion of the entire universe. The stress energy tensor, that thing your textbook reduced to just mass, contains the seeds of both the densest and most explosive phenomena in the cosmos. Mass was never the whole story. I want to bring Feynman back into the picture now, because his perspective on this question is characteristically honest and important. Feynman spent significant parts of his career thinking about the relationship between gravity and quantum mechanics, and he was unflinching about where understanding ends and mystery begins. He pointed out that general relativity tells us extraordinarily precisely how mass and energy curve space-time. The equations work. The predictions match observations to extraordinary precision. But why energy curves space-time, what the fundamental mechanism is at the quantum level, remains genuinely unknown. In quantum field theory, forces are mediated by particles. Electromagnetism is mediated by photons, the strong force by gluons, the weak force by W and Z bosons. Gravity, in this framework, and should be mediated by gravitons, spin two massless particles that couple to the stress energy tensor. But as we discussed in our previous video, every attempt to build a consistent quantum field theory of gravity using gravitons produces unmanageable mathematical infinities. The graviton, the particle that would explain why energy curves space-time at the quantum level, cannot currently be incorporated into our mathematical framework without breaking it. So here is the honest Feynman-level answer to the question: why does mass create gravity? Mass creates gravity because mass is energy. Energy appears in the stress energy tensor. The stress energy tensor curves space-time according to Einstein's field equations. And Einstein's field equations match every observation we have ever made. That is a magnificent answer, a profound answer, a deeply beautiful answer. And it is also, honestly, incomplete. Because we do not yet know why the stress energy tensor curves space-time, not at the quantum level, not in the way we understand, say, why electric charges attract and repel. Physics does not yet have that answer. And in that gap, in that beautiful, frustrating, exciting gap, lies some of the greatest physics yet to be discovered. I want to finish with something specifically for the Australian students watching this video. Whether you are studying HSC physics, VCE physics, or you are just genuinely curious, I want to say something important. The questions in this video: what is mass? Why does energy curve space-time? What is the quantum theory of gravity? These are not questions for future physicists to worry about. They are questions for you right now. In year 11, in year 12, at university. Because the habit of asking why, not just accepting the equation, is the most important intellectual habit in all of science. Your exam will ask you F equals mg. Your exam will ask you to calculate gravitational potential energy and orbital velocity, and you absolutely need to know those calculations. But the student who also asks, why does mass curve space-time, who understands that mass is energy, that pressure also curves space-time, that 99% of their own mass is binding energy, that student sees physics differently, not just as a collection of equations to memorize, but as a living, growing, genuinely incomplete map of reality. Australia has produced extraordinary physicists. Ruby Payne-Scott, pioneer of radio astronomy; Lawrence Bragg, Nobel Prize in X-ray crystallography at age 25, the youngest Nobel laureate in physics in history; the OzGrav team detecting gravitational waves. The next great contribution to understanding gravity, to quantum gravity, could come from someone watching this video right now, somewhere in Australia, asking exactly these questions. Do not stop asking. So let us bring it all together. Feynman style. Mass and inertial mass are distinct concepts, made identical by Einstein's equivalence principle. Mass itself comes, at the fundamental particle level, from interaction with the Higgs field, and at the composite particle level, mostly from the binding energy of the strong nuclear force via E equals mc squared. The source of gravity is not mass alone. It is the full stress energy tensor, energy density, momentum, and pressure in all forms. Pure light curves space-time. Pressure inside neutron stars adds to their gravity. Negative pressure from dark energy drives the accelerating expansion of the universe. E equals mc squared tells us mass is energy, and energy curves space-time. Why energy curves space-time at the quantum level remains one of the greatest unsolved problems in all of physics. The frontier, the edge of the map, and that frontier is waiting for curious minds to push it further. If this video rewired how you think about mass and gravity, smash that subscribe button and join the Curious Physics AU family. New videos every week built for Australian students and anyone who refuses to stop at the equation. Drop a comment below. What surprised you most? The Higgs field, the stress energy tensor, the fact that 99% of your mass is binding energy. Tell me what landed. Share this with your physics study group. This is the context that turns good physics students into great ones. I will catch you in the next one.